It's a famous example of resonance breaking a wine glass with your voice. Yes, it's possible. Notice that in order to do this, she has to sing at exactly the same pitch that the wine glass naturally will resonate at. Now, you can break a wine glass with your voice. That's an example of resonance. A more familiar example of resonance is just pushing someone on a swing. When you push someone on a swing, of course, the swing has a natural resonant frequency. It's basically a simple pendulum, and its frequency is square root of g divided by the length of the swing. Naturally goes to that frequency. To push someone on a swing, you just automatically push them at the same frequency that they naturally want to go at. If you try to push at a different frequency, they will move at that frequency, but reluctantly. And here's a pendulum example that shows resonance as well. They are driven by the same amount of force. What's happening here is the support point of the pendulum is being forced back and forth. Here's a low frequency forcing. It's at, I believe, 1/3 of the resonant frequency of the pendulum. It does move, but small amplitude. In the center picture, this force, which is driving it into motion, matches the natural frequency of the pendulum, and you see the result is a very large amplitude of motion. The third picture is at 4/3 higher than the natural frequency of the pendulum, and the pendulum does reluctantly vibrate at that frequency, but with a much smaller amplitude. So it shows you the magic of resonance, which is if you hit the natural frequency that the system would like to vibrate at naturally, then a large amplitude results out of it. We do all that intuitively whenever we push someone on a swing. So what we're talking about here are driven oscillations. Driven oscillation, for example, a mass spring system. You've got a spring, you've got a mass. There's always some damping that's present. Here's our damper with some fluid in it attached to the mass. The new ingredient is that there's now some external force which acts on our mass directly and actually vibrates the mass back and forth. So there's some now F external which acts on our mass, and that is the driving force, hence the name, a driven oscillation. So what is Newton's law going to look like for this kind of system? Well, you've got ma is equal to, you've got the force of the spring acting on the mass, minus kx. The damper is present, minus B times V. And now the new ingredient is we have an additional vibrating force that's acting. The vibrating force has an amplitude to it, which I'm calling F max. And it's a vibrating type force, so it's a sinusoidal type of force, cosine omega t. It could be sine, cosine, or any phase in between sine or cosine. So notice in this problem, omega is referring to the frequency that the driving force is vibrating at. It's not necessarily the natural frequency, unless you happen to be at resonance. So we've seen the big deal with resonance is that the amplitude of oscillation is maximized if the driving frequency, omega, is equal to the natural frequency, which we've called omega naught, of the oscillator. That's what's called resonance. Resonance. So summarizing that again, resonance occurs if the driving frequency, omega, equals omega naught. Your text may call it omega sub d for driving frequency, but that may also be confused with the damped frequency, So go back and review that. I don't want to label it, just call it omega. It's the frequency of the driving force. So resonance will occur if you hit that magic natural frequency. Also, there's another thing which happens when you're at resonance. Think about when you push someone on a swing. When do you push them the hardest? Is it when they're at the top of their swing, coming back at you? No, it's not. You push them the hardest when they're moving the fastest through the equilibrium position. Now, why do we do that? We do it intuitively. We do that so that we're pushing the hardest when their velocity is the greatest. Why would we do that? We intuitively maximize the power that we are giving to the vibration. Remember that force times velocity is power. So we'll explore that in a moment. But the other special thing that happens at resonance is that the external force and the velocity of the oscillator are in phase. So when the force is big, that's when the velocity is also large. That only happens when you're exactly at resonance, matching that natural frequency. To be clear, what I mean by in phase, I mean that if the force, which I'll put in blue, if the force is, say, a cosine, then I'm drawing them versus time, and this is F external. Then the velocity is in phase with it. The velocity is large whenever the force is large, and that's V. These are both drawn as a function of time. So what I mean by they're in phase. So in other words, if the driving force is like cos omega t, at resonance, the velocity is also cos omega t. Okay, so now we'll use all these things to learn what we can specifically about resonance. Like, for example, how big is the amplitude going to get when you drive the system at resonance? Let's think about energy. At resonance, you are um, being most efficient at giving energy to the oscillator. If you go at the wrong frequency, the amplitude doesn't get as big, and you're not being as efficient at giving your energy into the system. But at resonance, you get that huge vibration out of it, and you're giving the most energy possible to the system. You can tell because the force and the velocity are in phase with each other, and you're maximizing the amount of power which you're feeding into the system. Okay, so let's look at power then. Let's look at first at the power which is given by the external force. We'll call it P external. This is the wattage of the motor which is driving the system. Okay, I'd like to figure out what it is. All right, so power from that external force is that force multiplied by the velocity of the vibrator. That's how we compute power. Work, energy is force times distance. Power is force times velocity. Okay, so let's calculate what this is. This is F external. This is F max. I'm just plugging in. F external is F max cos omega t. The velocity is omega x max, or just amplitude, but I'm going to call it x max here. And then both of them have a cos omega t term. They're in step with each other, in phase, so I get cos squared. Okay, so the amount of energy being put in vibrates. There are some moments where the velocity is zero and the force is also, there's some moments where the force and the velocity are both zero, so there's no energy being put in. What I'd like to do is just average it out. So I'll average, using this symbol means average. I'll look at the average power that's put in over a whole cycle. Now, these are just constants. They just factor out. I need the average value of cosine squared. What's the average of cosine squared? To see that, here's the graph. In black is the graph of cosine. One full cycle of cosine is shown in black. I need to look at the average value of cos squared, which is the curve in red. From the symmetry of the graph, you should be able to, I guess, have an educated guess that the average value of cosine squared is exactly 1/2. Now, the average of cosine is definitely 0. It goes up and down below 0 to average out to 0. But the average of cosine squared is exactly 1/2. We'll use that over and over in this course when we talk about vibrations, averaging out cosine squared to be 1/2. So we learned that the amount of power being put in from the external driving force, this just gives me a 1/2. So I have 1/2 F max times omega times X max. Remember, X max, it just means the amplitude of the oscillator. Okay. Well, we're kind of stuck. It doesn't tell me that much because although I might know how big the driving force amplitude is, I'd like to be able to predict how big the amplitude is. So what can we do? Well, in a driven oscillator, the energy being put in from the external driving force must just exactly be balanced by the energy being lost due to the damping. In other words, I'm going to set the power from the driving force to be exactly equal to the power that's lost due to damping. Let me show the driven pendulum again. You see the driving force keeps putting in energy over and over and over and over. But the amplitude's not getting bigger and bigger and bigger because the energy being put in from the driving force is just exactly being lost from the energy lost from the damping force, from the presence of the air around it that loses the energy. Otherwise, the amplitude would keep getting bigger and bigger and bigger and bigger, which it doesn't. It just settles down to a stable amplitude. In this case, it's small. At resonance, that stable amplitude is very large. But regardless, for any driven oscillator, at resonance or not, the power that's lost from the damping must exactly balance the power that's being put in from the driving force. Okay, so first I'm going to calculate the power that's being lost due to the damping. So it would be the force of the damping multiplied by the velocity. That would be minus BV, that's the damping force, multiplied by the velocity, that gives me V squared. So let's plug in, that's minus B. The velocity, now if I'm at resonance, remember the velocity is in phase with the driving force. So it would give me omega squared, X max squared, cos squared. Where did that come from? Why omega squared X max squared? Well, remember that the velocity of an oscillator is omega X max times cos omega t. So I just plug that in. Like before, I really want to just average it over a cycle. So I average everything, and again, I have to then average cos squared, which has an average value of 1/2. So I get minus 1/2 B omega squared X max squared. That's the average power that the damping force loses on each cycle. Okay, now remember that resonance or not, the energy being put in by the external force must exactly balance the energy being lost by the damping force. So what I should do is set these two expressions equal to each other. Resonance or not, they're going to be identical. The power input from the external force will match the power that's being lost from the damping force. So I'll set them equal to each other, and what do I learn? Well, I'll learn, notice I can, by setting them equal, I should say they're not exactly equal, they're equal and opposite, because power being put in by the driving force, equal amount of power being put out, lost from the system by the damping force. So they're equal and opposite. I'll set the, cancel out the minus sign and set them equal to each other. It lets me solve for how big X max is going to be. Basically setting the two expressions equal and solving for X max. And I learn that there's a simple relationship that tells me how big the amplitude will get at resonance. It's going to be equal to F max divided by B omega. A very simple equation that tells me that if I know how big the driving force is, I can now predict how large the amplitude when it resonates is going to be. Call it the resonant amplitude. I'll remind you, this does not apply if you're off resonance. If I'm off resonance, I can't use that equation to figure out how big the amplitude is going to be. The equation hinges on using the condition of resonance, that the force and the velocity are in phase. It lets me predict how big this very large resonant amplitude will be in terms of the driving force. Now that I know that, I could plug back in and get expressions for the power being put in from the driving force. Now that I know how big X is, I can go back and figure out the power external. Let's do that. The average power from that external driving force. You see it's here. It's 1/2 F max omega X max. If I plug in the expression for X, you'll see that it's just simply 1/2 F squared divided by B. And so that's a useful equation. Lets me figure out how much power is needed to actually drive the resonance. Doesn't even depend on the frequency either. So next up, we'll do a couple examples of driven oscillators. Here's our first resonance example. A car with passengers drives over a washboard dirt road. Means there are evenly spaced bumps in the road. The bumps are 4 meters apart, and we're told that the car bounces with maximum amplitude when its speed is 16 kilometers per hour. In other words, the timing between the bumps on the road, when you drive at that speed, must match the resonant frequency of the suspension of the car. The question that's ultimately asked is, how much does the suspension rise when the people get out of the car? Okay, we'll deal with that part of it next. Let's just look at the resonance part of the problem first. So what we know here is the timing of the bumps. In other words, the period of the periodic driving force that comes from hitting the bumps in the road. The timing must be the distance between the bumps divided by the speed. That's the time from one bump to the next. Okay, what the point of that is, from that I can figure out the frequency of the driving force, omega. Omega is going to be 2 pi divided by that period timing. 2 pi over t. So that comes out to be 6.98 radians per second. That's the driving force frequency, the frequency of the driving force. That must also be equal to the natural frequency of the suspension of the car. You see, I'm thinking of the car as basically a bunch of mass being suspended by 4 springs. Something like that. So the bumps as it moves along, it hits the bumps periodically. One bump, and the next bump's coming in over here. And have the timing between them. It must be that the driving frequency is matching the natural frequency. So I know that this is also equal to omega naught. It's resonance. So what do I know about the natural frequency of a mass on a spring? Well, I know that omega naught is equal to root k over m. Or actually, what I care about in this problem is really the value of k. So let me phrase it that way. K is equal to m omega squared. That's just omega naught is root k over m. I'd like to solve for k because that's going to determine how stiff the springs are. And I get a value which is 9,270 newtons per meter. By the way, this isn't actually the K for each individual spring. It's the combined K from all 4 of them together, which is what I really care about. What mass did I plug in here to get this answer? This is the total mass. Let me actually call it M total. Let me spell it out better. It's the mass of the car plus the mass of the 4 passengers. All the mass, total mass. Okay, so from that, that's how I got the K value, 9270 newtons per meter, the force constant of the combined shocks on the car. Okay, now that I know how stiff the suspension is, now I can figure out how much it'll rise when the people step out of the vehicle. You see, initially, there's the mass of the car and the 4 passengers. But when they step out of the car, of course, the suspension rises, and now the car is up here, not drawn to scale, but now the springs are not as compressed anymore, because now it's only the mass of the car. The people have stepped out. Okay. Remember that F is equal to minus kx. That x is the compression of the spring. Now, in this case, the force changes, and I'd like to know how much the x, the extension, changes when they step out. Well, since F is equal to minus kx, that means the change in F is equal to minus k times the change in the extension, which is what I have here. I can figure out how much less force there is on the springs, and lets me solve for delta x. So delta x will be equal to the change in force, which is minus 4m. The minus sign will cancel, so it just comes out to be 4mg. That's the change in force. 4 masses step out times g gives me their weight, and I divide that by k, and there's our answer. Comes out to be about a foot, 0.35 meters. That's the change in extension when they step out of the vehicle. Here's a driven oscillator. What's going on here is we've got, it's a mass hanging on a spring, but the support point of the spring right here, that point is vibrating. That's what's feeding energy into the system and drives the system to vibrate. Of course, left on its own, it would vibrate at its own natural frequency, root k over m. But now we have the support moving that's going to drive the oscillation. So we're given the mass and the force constant of the spring, and we're told exactly how the support moves up and down versus time. S of t is sine of 10 pi t. Y is the position of the mass from its equilibrium position. Question A, write down Newton's second law, which determines how the position changes with time. Then we'll identify what the driving force is, and should the support vibrate with a higher or lower frequency to achieve resonance? Okay, so first, let's look at Newton's law. The mass times acceleration of the mass is equal to the net force that acts. Okay. Now, the only thing besides any damping that's around, the only thing that acts on the mass directly is the spring. The motion of the support is kind of an indirect thing. Okay. So, how do we account for that? Well, you see, the only time the spring pulls on the mass is if the spring is stretched. So if the mass happens to move down, say 1 inch, at the same moment, the support has also moved down by 1 inch, then the spring isn't even stretched at all. You see, the only time the spring is stretched is if there's a difference in motion between the support and the mass. In other words, I'm just using Hooke's law. The only force that acts on the mass, besides damping, is Hooke's law from the spring, which is minus k, and I'm just going to write it out, multiplied by the extension of the spring. We'll figure out how to write that extension down in a moment. And then there's the possible damping force minus BV. Okay, so the question is, how big is the extension of the spring? It's not just the y value. By the way, the picture shows capital Y, it's lowercase y. It's supposed to be the same thing. So the extension of the spring is not just how far the mass has moved down from equilibrium. You have to subtract off the S value as well. In other words, the extension of the spring is actually y minus S. That, you see, in other words, another way to say it is, it's the relative motion of the mass and the support which tells you whether the spring is stretched or compressed. So I got to plug that in. So I get minus k, y minus S gives me minus k times y, plus k times the function S minus BV. And notice what we have right here. That is our driving force term, because it's an extra force that's being applied to the mass. It's not just the minus k times y. There's an extra piece here, and here's the damping. This extra piece is a vibrating force term. That's our driving force. So now we can answer part B. Identify the driving force. F external. It must be just k multiplied by the function S, which is given here. The value of k is known to be half a Newton per meter. So this is 0.50 newtons per meter, multiplied by the function S. Now S is in meters. So the amplitude there, this really means 1 meter multiplied by sine omega t. So this is 1 meter times sine omega t, so it's 10 pi t. Okay. So simplifying a little bit, this is 0.5 newtons multiplied by sine 10 pi t. So there's our external driving force. It arose kind of indirectly because the support's vibrating up and down. that causes an extra stretching of the spring, which now we figured out what the effect of that support motion is. To give a force whose amplitude is half a newton, and here's the sinusoidal part of it. So we've identified the driving force, and here, by the way, is the driving force amplitude, half a newton. Question C. To achieve resonance, what do we have to do? Is it already at resonance or what? How do I know that? How do I know whether the system is resonating or not? You have to compare omega, the driving frequency, with the natural frequency. So let's see what the natural frequency of the system is, omega 0. It's the square root of k divided by m. K is half a newton per meter. The mass is half of a kilogram, so I get 1 radian per second. That's the natural frequency of the system. Is the driving force going at 1 radian per second? No, it's 10 pi radians per second. So in fact, omega, the driving frequency, which is it's 10 pi radians per second, that's like 30 radians per second, way bigger than 1. That is much greater than omega naught. Therefore, you'd better lower the driving frequency in order to achieve resonance. So it's not at resonance. I couldn't use any of our equations to figure out the amplitude of the motion or any of that. However, if we changed the frequency, so it was at resonance, so dialed it down from 10 pi to 1 radian per second, then you'd be at resonance. In that case, you could figure out x max. So in other words, the equations like x max is equal to f max divided by b omega. I can't use that right here in this problem. This is only for the situation of resonance, which our system is not.